Welcome to qnawire.
We're going to consider a 2 kilogram mass stacked on top of a 7 kilogram mass shown over here. And we know that both of them are attached to a spring. So they're going to have an simple harmonic motion when the spring is going to be compressed or stretched. And we want to know that given the values of the coefficient of static friction in between the masses and the spring constant of the 200 newtons per meter, we want to know what is the maximum amplitude of the simple harmonic motion. So the consideration is that the system shown below, what needs to happen is that the top mass is not going to slip during the oscillation. Thus, what we're going to have is that the force diagram corresponding to this small mass is going to be the normal force going up, mg going down, the applied force, and the friction, force of friction. So, according to this diagram, what we're going to get is that the sum of the forces on x needs to be equal to 0 for the system to not move or to not slide of this light. So that means that the applied force minus the force of friction needs to be equal. For this condition, the applied force needs to be equal to the force of friction, and the force of friction is equal to the normal times the coefficient of static friction. The normal is going to be equal from the sum of the forces on y equal to 0. We know that this is equal to normal. Sorry about that. This is equal to the normal minus mg. So the normal needs to be equal to mg in this case. So the force of friction is going to be equal to mg times mu s. So the maximum applied force needs to be equal to mg times mu s, the coefficient of static friction. But this maximum applied force can come from the acceleration due to the harmonic motion. In this case, the harmonic motion is going to involve both of the masses. I'm going to label them m plus m. So this max applied force is going to be equal to m plus m times the acceleration, the maximum possible acceleration that we're going to have. So the maximum acceleration is going to be equal to mg times coefficient of static friction divided by m plus m. Now, with this maximum acceleration, what we can say is that according to the equations of motion for cyclic harmonic motion, what we're going to get is that the position as a function of time, we can look at it as a times cosine of omega t. The velocity as a function of time would be equal to minus omega a times sine of omega t. And the acceleration as a function of time would be equal to minus omega squared amplitude times cosine of omega t. This is part of the harmonic motion. And over here, what we're going to get is that the maximum acceleration is going to be given by omega squared times the amplitude of the motion. So we can equate both of these parts over here. From here we know that omega squared a is going to be equal to mg, coefficient of static friction, divided by m plus m. Remember that the value for omega squared for simple harmonic motion is going to be equal to k over m. In this case, it would be the sum of both of the masses, since both of them are going to be attached to the spring. So the amplitude is going to become equal to mg times coefficient of static friction divided by m plus m divided by omega squared, right? But 1 over omega squared is going to be equal to k m plus m. Both of the masses are going to cancel out, and the maximum amplitude would be equal to mg, coefficient of static friction, divided by our spring constant. Recall that the small m was for the small block, which is of 2 kilograms, so in this case 2 kilograms times 9.81 meters per second squared times the coefficient of static friction, which is 0.45, and divided by the spring constant, that is 200 Newton per meter. As you can see, mass times acceleration is Newton, and Newton with Newton are going to cancel out, and we're going to get the final result in meters equal to 0.044 145 meters, which in centimeters corresponds to 4.4145 centimeters. This would be our maximum amplitude. And now for the energy. So far we have calculated the maximum amplitude, part A, and B, we want to know what is going to be the total energy of this system under these conditions. So remember, this is going to be our maximum amplitude. So the maximum energy for this system is going to be equal to 1/2 of k times the maximum amplitude, the maximum potential energy that we're going to be able to have. So this is going to be 1/2 of k, 200 Newton per meter. Sorry, amplitude squared, maximum amplitude squared over here. Times the amplitude, I'm going to put it in meters, 4.4145 times 10 to the minus 2 meters squared. So the energy becomes 0.19488 joules, or up to 3 significant digits equal to 0.195 joules. Let me make this 5 a little bit more like a 5 to not get confused. Okay, so in summary, what we did was first of all calculate what is going to be the maximum possible applied force. Then we can relate that applied force to the acceleration of the system connected to the spring, which is the two masses. And with that maximum acceleration, we're going to employ the equations of motion coming from the simple harmonic motion. So all of this is simple harmonic motion, or a simple harmonic oscillator. So the maximum acceleration from this equation of motions is going to be given by this factor over here. Remember that the cosine function goes from -1 to 1. So the maximum value is omega squared times a. We know that omega squared is equal to k over the mass. The total mass that is experimenting the motion is the small one plus the big mass over here, m plus m. And with that, we have omega squared times a. We solve for a doing this substitution. We get the value for the maximum amplitude, and with that we can calculate the total energy as 1/2 of ka squared, which is the maximum potential energy that we're going to have on the system. And with that, it would be all. Thank you very much and have a good one.